right, all you biochemists out there, welcome back to another online lecture, actually. So we're going to go ahead and talk about Chapter 11, Introduction to Organic Chemistry, one of my favorite topics to talk about. So we're going to go and start talking about hydrocarbons. What are the two words that you kind of hear when you hear the word hydrocarbon? Hydrogen and carbon atoms. So that will become very important later when trying to determine what a hydrocarbon is. Let's go ahead and get started. Firefighters must be knowledgeable about the fire codes and uh, arson and the handling of disposable and hazardous materials. And since firefighters also provide emergency care for the sick and injured people, they need to be aware of emergency medical and rescue procedures as well as proper methods for controlling the spread of infectious diseases. So let's go ahead and get started. Organic chemistry is a study of carbon compounds. Now, organic compounds such as vegetable oil contain atoms such as carbon and hydrogen right over there. So you can see we have vegetable oil there mixed in with water. As you can probably already know, if you were to mix water and oil together, they will not mix together at all. No matter how hard you try to shake that vial, no matter how hard you try to shake that test tube or that cup of oil and water, it will never stay mixed ever. Okay, at least oil and water alone. An organic compound is a compound made of or from carbon and hydrogen atoms. It may also contain other nonmetals such as oxygen and sulfur, nitrogen, phosphorus, or even a halogen, and is often found in common products such as gasoline, medicines, shampoos, plastics, and perfumes. Now, the formula for organic compounds are often written with the carbon first, then the hydrogen next. That X and Y indicates the subscripts right over there, and then anything else after that. So C something, H something, and then whatever is after that. For example, C6H12O6. If you guessed it, that's a glucose molecule and is an organic molecule. Okay? Now, organic compounds typically have covalent bonds, low melting and boiling points, and are flammable and undergo combustion but are not soluble in water. So, for example, as you already know, vegetable oil is a mixture of organic compounds and is definitely not soluble in water. Now, many inorganic compounds, in contrast, have high melting and boiling points. Inorganic compounds that are ionic are usually soluble in water if they're ionic, and most of them do not burn in air. For example, propane. Propane here is not an example of an inorganic compound because it contains carbon and hydrogen. Propane, pro stands for 3. So we have here C, C, and C covalently. Shoot, this drives me insane. Right over there. And then we have here at each of these little lines, I'm not going to draw them out because my pad is driving me insane. But as you can see, each of those little sticks that are sticking out of the carbon is attached to a hydrogen atom. Okay, that is an organic compound. Sodium chloride is table salt. It is not organic because it does not contain carbon or hydrogen in it. Rather than it consists of just sodium and chlorine ions. Sodium chloride you will get so sick of hearing this compound because it is all over this book because it is the poster compound for many of the different properties that you'll be studying in chemistry. Now, here's a table that compares organic versus inorganic compounds. For example, the elements that are present in organic compounds, carbon, hydrogens, and sometimes other nonmetals as well. For example, we have here propane versus inorganic contains most metals and nonmetals such as sodium and chloride. Now, the particles or organic compounds tend to be connected together in form of molecules versus that of inorganic compounds in the form of ions. Now, its bonding is mostly covalent versus that, for example, in propane, it is covalent versus that of sodium chloride. It is mainly ionic, although there are some covalent ones out there, some exceptions to the rule. And as you can see here, sodium chloride is an ionic compound. The polarity of bonds here, they tend to be nonpolar unless strongly electronegative atoms are present there, which is strongly indicative of a possible functional group on that molecule. And for example, propane right over here is a nonpolar molecule. And then we definitely have here sodium chloride, which is ionic, which contains mostly ionic and polar covalent, although there are a few nonpolar covalent ones there. I am periodically, you might see me go in and grab for a cough drop because this is going to be One long lecture indeed. Now, sorry guys, I need it in order to talk. Now, the polarity of bonds here are non-polars and strong. Melting points here are usually very low for organic compounds versus inorganic are usually very high. Same thing for its boiling point. Okay, the flammability for organic compounds tends to be very high versus that of inorganic compounds tends to be very low. And the solubility in water is not soluble unless we have polar groups present there versus that of ionic or inorganic ones that tend to be soluble unless you have nonpolar molecules or substituents in that molecule. So if you were to identify each characteristic as most typical of compounds that are inorganic or organic, which one would it be? So if we were to look at the answers here, high melting point would be inorganic, not soluble in water would be organic, has a formula right here is organic, magnesium chloride is inorganic, burns easily is organic, and has covalent bonds that would be organic. All right, the word hydrocarbons are organic compounds that contain only, guess what? Hydrogen and carbon. In organic molecules, every carbon has 4 bonds. And this is a very important property because, as you remember, carbon has 6 electrons to them. We have here 1 and 2. Oh, shoot, come on. 1 and 2 right over there. And then we have here in its valence shell 3, 4, 5, and 6. These 4 electrons that you see right around here are capable of forming 4 covalent bonds with other molecules out there. A saturated hydrocarbon means that it is a molecule where every single carbon contains only a single bond. That means that every one is single bonded to something. That's a saturated hydrocarbon. In this case, if it's a hydrocarbon, the only thing it can bind to is either a carbon or a hydrogen atom. You can see each of these carbon atoms still maintains that 4 covalent bonds that it does have here. Okay. And for example, methane. Here's is the molecular electron dot structure here of methane. You can see its valence shell right over there. It is bonded to 4 hydrogen atoms. If we were to look at the expanded structural formula right over there, we can see very commonly drawn in textbooks. Or if you were to do the ball and stick model, take a look at this ball and stick model. You can see here the angle between each of these hydrogen atoms is 109 degrees. That is very, very, very important. Right over there. Ethane. Meth is 1. Eth means 2. So you can see ethane here has 2 carbons. Each tetrahedral carbon forms 3 covalent bonds to hydrogen and 1 other carbon. You can see here, look at its ball and stick model. You can see we have each carbon here in its tetrahedral form. Meth is 1. Eth is 2. Prop is 3. But is 4. You can see here we have a butane molecule, C4H10. If you can predict the shape around each carbon atom, it's definitely going to be a tetrahedral shape because they all have single bonds. There are 4 single bonds, so each one of those carbon atoms automatically tells you if there's no other outside forces interacting with it, like I could bend this pen if I want. I'm not going to do it, but it should be straight. If I were to put enough force, I could definitely bend this pen. Same thing here with this molecule. If there are no outside forces interacting strong enough that is interact with this, it will definitely be a tetrahedral shape. Okay, alkanes. Let's go ahead and talk about the different kinds out there. By the way, for those of you guys who are asking me about this in lecture, I have here a very important chart. It is a summary of functional group nomenclatures when naming organic compounds. This might be helpful for you. You might want to write this down or take notes on this. These are the main groups in order of decreasing priority. There are these things known as functional groups, where these groups can react with other kinds of molecules out there. We're going to get to them in a little bit, but you might want to keep a note of this particular chart, especially when naming organic compounds in their order of priority. And these are ordered in terms of reactivity, meaning that the carboxylic acids are the most reactive. We'll get to it later in the lecture. Esters are next, amides are next, nitriles are next, aldehydes, ketones, alcohols, then amines, alkenes, then alkynes, then alkanes, then ethers, and then halides. This is the order of reactivity. So the top being the most reactive, the bottom meaning the least reactive in terms of naming. Okay? And in terms of priority. And tends to be in the order of reactivity. All right, let's move on. Now, a large number of carbon compounds are possible because the covalent bond between the carbon atoms, such as those in hexane, meth, eth, prop, bute, penta, hex. Okay? Hex is 6. So you can see we have our ball and stick model of a hexane molecule. There's 1, 2, 3, 4, 5, 6 carbons. And we have there 14 hydrogens. Each one of these carbons has 4 bonds to them. Now, alkanes here are hydrocarbons that contain only carbon-carbon or carbon-hydrogen bonds and are formed by a continuous chain of carbon atoms. Now, there is an International Union of Pure Applied Chemistry which is used to name these compounds, and alkane molecules tend to have the letters A and E at the end of them, ane, as its suffix. And we use the Greek prefixes to name carbon chains with 5 or more carbon atoms. So once again, check out this list. Repeat after me. Meth is 1, eth 2, prop 3, bute 4 carbons, pent 5, hex 6, hept H-E-P-T is 7, oct is 8 like an octopus, non is 9, and dec is 10. Okay? Dec is 10. That's why when you move 1 decimal over, you're decreasing it or increasing it by a 10-fold value. Dec, decimal. Okay? So you can see here we have different alkane molecules. Right here we have methane, which is 1, ethane is 2, propane is 3, hexane is 6, octane is 8, and decane is 10. Now, can you imagine if we were to draw every alkane molecule out there in its condensed form? I'm sorry, not its condensed form, it is in its expanded structural formula right over there. As you can see, that would be very laborious, a lot of time, a lot of work. Nobody wants to do that. And so there is an alternative way in which we can write this molecule, and that is known as its condensed structural formulas. You can see there that same butane molecule. Now, rather than drawing little lines that resemble covalent bonds out there in its expanded form, we can cut it down: CH3-CH2-CH2-CH3, and those hydrogen atoms are implied to be in a tetrahedral shape. Okay, that would be a butane molecule. You can see right over here, alkanes are written with structural formulas that are expanded to show each bond and then condensed to show each carbon atom and its attached hydrocarbons. You can see here, if we were to expand the terminal end of an alkane, the end, we have here 3 hydrogens covalently bonded to a carbon. You can shorthand this in its condensed form as a CH3 or a methyl end. If we were to use something in the inner regions of that molecule, we have here C and 2 H's, we can shorthand it here as just CH2. So just kind of keep those two separate right over there. Now, alkane compounds can be represented by their molecular formulas, which give the total number of carbon and hydrogen atoms. What's even more convenient is this skeletal form, which shows a carbon skeleton in which carbon atoms are represented at the end of each line or each corner or vertice. As you can see here, we have a skeletal formula. We have 1, 2, 3, and 4 different vertices. Each one of those vertices is implied to be a carbon, and if it doesn't have an oxygen or any sort of substituent indicated, we can assume it's a hydrogen. Because let's face it, hydrogen being the smallest atom out there, nobody wants to sit around and draw little hydrogen atoms everywhere. So in science, it is implied. Okay. Now, amazingly, carbon atoms in a chain connected by single carbon-carbon bonds can rotate. So groups attached to each carbon can move freely about the carbon-carbon bond. So take a look at this. We have here, think about it in 3D. We have a butane molecule right here, meth, eth, prop, bute. There are 4 carbon atoms here. And if you were to put the ball and stick model together for this particular compound, you're going to get something that looks like this. The carbon-carbon single bond right here is fully capable, because it's not a double bond, it's a single bond. It can rotate each of these two groups right over here. Okay, as you can see in our example, it's only rotating one of those groups around and around and around. So I'll show you guys that in lecture when I have a molecular models kit, but it will definitely rotate around and around and around. Now, as a methyl group rotates, methyl here, methane or methyl group rotates about the single carbon-carbon bond. They appear at different angles. That will become extremely important a little bit later. Now, a hexane molecule can be represented in several different ways. You can have the molecular formula. We can have the, which is right here. We can have the ball and stick model. We can have the expanded model. We can have the condensed model, and we can definitely have its skeletal. Most commonly, you're going to see it in its skeletal formula, because it is clearly the easiest and most convenient to draw. You should know all of these ways, 5 ways in which to resemble a particular molecule. In the event that on an exam I may ask you, draw this or that. Once again, here is another representation of each of those models right over there. This is for butane, C4H10. The molecular model formula will be right here, C4H10. Expanded structural formula is here, ball and stick. Condensed structural formula. Now, here's the thing about the condensed structural formula. There are many different ways in which you can draw butane, and you can see there it's drawn right over here. Most commonly, you're going to see it looking like this or looking like that. These are most common, but either one of those would be fine. And the skeletal formula is my most favorite because it's the easiest to draw. You might see it looking like that there. All right, given the expanded structural formula, provide the molecular formula, condensed structural formula, and then the compound name. So as you were to see a molecular 1, 2, 3, 4, 5 carbons, so this is a pentane molecule. And its condensed structural formula here is CH. Okay, well, CH3, CH2, 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 and CH3. Pentane should have been the compound name right over there. Guys, it is 1:15 in the morning, and I am dedicated to finishing this lecture for you guys. All right, and its molecular formula is C5H12, so just kind of a correction check right over there. Here's a condensed structural formula, and of course, the compound name is pentane. Now, write the condensed structural formula for ethane or heptane. You can see here ethane has 2 carbons in it, CC, and then of course the rest would be hydrogens, and then heptane would have 7 carbons, 1, 2, 3, 4, 5, 6, and 7, and then the rest of the bonds will be filled with hydrogen. Talk about cycloalkane. Cyclo, what does cyclo sound like to cyclo sounds like a bicycle, because it is kind of looking like a wheel or a cyclic compound. So these are cyclic alkanes and have 2 fewer hydrogen atoms than the open chain form. And the reason why, as you can see here in propane, we have CH3, but in order to get these 2 to connect together, we've got to lose a hydrogen atom there in order to afford to make that bond. This cyclopropane has a lot of torsion in it, a lot of strain in it. Cyclohexane is the one that's most stable because it works with the tetrahedral shape. But anything less than that, there's a lot of torsion, and there's a huge tendency for this molecule to want to bust open there. Now, in order to indicate that in a molecular sense, the prefix cyclo is indicated there to tell us that we're talking about a cyclo compound. So we have here the ball and stick model for a cycloalkane. In this case, it's cyclopropane. Propane has 3 carbons in it, guys. We have here cyclobutane, cyclopentane, and then we have here a cyclohexane molecule. The most stable of all of the cyclos out there is a cyclohexane. And you can see if we were to look at its condensed structural formula, you're going to get it looking like this. And of course, I love the skeletal formula because it is the easiest there to draw. Okay. All right, let's go ahead and give the IUPAC names of each of these following compounds we have here. 1, 2, 3, 4, 5, 6, 7, 8. So that is an octane. octane molecule, octane. And the next one here is 1, 2, 3, 4, 5 vertices, and is in a wheel form or cyclo form. That's the cyclopentane, octane, cyclopentane. You can go ahead and name the following compounds in your notebook or on your own, and the answers are given there. Now let's face it, these are very basic molecules, very boring molecules. What makes a molecule, especially an alkane, very interesting are the substituents or the groups that are attached to them. So a substituent, the atoms can be arranged so that a side group called a branch or substituent is attached to a carbon chain. And then therefore, because this molecule is capable of forming that, they're known as structural isomers, meaning they have the same molecular formula but different arrangement of atoms because they are different structurally. So they have the same number of atoms bonded but in a different order. For example, butane has 2 structural isomers. You can make this, which is in its straight form, or you can make it in its branch form. They still have the same molecular structures. There's C4, and then we have here 3 plus 2 is 5, and then 10, H10. And same thing here, we still have C4 and the H, let's count them, 3, 6, 9, and 10. We still have H's. These are structural isomers. Same molecular formula, but different way of arranging the bonds. So draw the 3 possible structural isomers of pentane. As you can see here, we can have it in its straight line form. We can have one substituent right over here at that second carbon, 1, 2, 3, and 4. And then we can even have it here in 1, 2, 3, 4, 5 carbons, the central carbon here attached to 4 different methyl groups right over there. Okay. So these are the different structural isomers. Same molecular formula, but different arrangement of the bonds and the atoms. Now substituents, once again, are atoms or groups of atoms attached to the carbon chain and include alkyl and halo groups, like halogens. Now an alkyl group are groups of carbon atoms attached to the carbon chain, and as you heard me mention earlier, methyl, heard me use the word methyl, we have that YL ending right over there. Now halogen atom halo substituents are halogen atoms attached to the carbon chain, and these are named as fluoro, chloro, bromo, or iodo. For example, some examples of methyl group is a CH3 substituent. Ethyl has 2 carbons, a propyl has 3, so you get the pattern here. An isopropyl has equal number of carbons on both sides of a particular kind of one here. So there are 3, 1, 2, 3. It's iso because the left and the right side contain the same number of carbon substituents. And of course, if we were to have fluorine, chlorine, bromine, and iodine, we would have fluoro, chloro, bromo, and iodo. For example, if we were to give the IUP AC name of this compound, first of all, we want to write the alkane name for the longest carbon chain of carbon atoms. So step number 1, determine the longest carbon chain. Step number 2, the number of the carbon atoms starting from the end near a substituent. Because why? That gives the nearest substituent a lower carbon value number, and I'll talk about that later. And give the location and name for each substituent in alphabetical order as a prefix to the name of the main chain. So for example here, we have this particular compound. First step here is to identify the longest carbon chain. So as you can see, this will be the longest carbon chain. Some of you might have said, well, what about this way? Well, that one only has 1, 2, 3, and 4 carbons. We can go a little longer by doing this one. So I'll have 6 carbons. Definitely know that's a pentane. We're definitely dealing with a pentane. Now let's go ahead and number them based on substituent. Number the carbon atoms starting from the end near the substituent, and then give the location name of each substituent in alphabetical order as a prefix to the name of the main chain. So if we were to order it from left to right, 1, 2, 3, 4, 5, therefore the chloro will have the lowest number, and it starts with a C. So it would be 2-chloro. That number 2 there indicates the position, what carbon it's on. 3-methyl because this methyl group is attached to that third carbon, propane. So it's 2-chloro, 3-methyl, propane. Why don't we go the other way? 1, 2, 3, 4, 5. It is possible, but the problem here is that we would have a 3, 4. Okay, it would be 3-methyl, 4-chloro, 3-methyl, and so therefore that would not give us the lowest numbered carbon. So we always want to order our numbers in order to give the lowest number of the carbon. Let's go ahead and name cycloalkanes. When one substituent is attached to a carbon atom in a cycloalkane, the name of the substituent is placed in front of the cycloalkane name. No number is needed for a single alkyl group or halogen group. The reason why, because when identifying the longest carbon chain, same thing. In this case, we're going to keep it to the cycloalkane because that is our molecule there. In this case, it is a cyclohexane. It could technically be, you could say 1-ethyl, because that is a 2-carbon. That's an ethyl group there. You could say 1-ethyl, but the 1 is implied when you say ethyl cyclohexane, because what other place could it be? It's a 1. And so therefore it is ethyl cyclohexane. Haloalkanes here are alkanes with a halogen atom that replaces a hydrogen atom and are named by putting the substituent in alphabetical order. Now, as you remember here from my little chart, halides have a lower priority compared to that of alkanes. So therefore, the alkanes here will take more precedent, not the halides. Okay. Okay, and they have the halogroup number according to the carbon where they are attached to the alkane. For example, we have here CH3 and a Cl. It is a methane molecule, and we have here a chloro, so it would be chloromethane. We have here a bromoethane because that Br, bromine atom, is attached there to that carbon. It doesn't matter which carbon because no matter which way you number it, it's going to be 1 on that bromo. So it's implied. You could label it 1-bromoethane, although you might get some laughs out of that. Or you can just say it's common ethyl bromide. Same thing here. 1-fluoropropane. You need to say 1-fluoropropane in this case. It is because we have no clue if you're talking about this carbon or that fluorine atom could attach to that second one. We don't know. So you must be specific and say 1-chloropropane so that the person who's reading that will know where to put that halogen. All right. Now, when drawing the formula for alkanes, the IUPAC name gives all the information you need in order to draw a condensed structural formula for the alkane. For example, 1-chloro, 1,2-dimethyl heptane. So check this out. Di means 2 because we want to make sure we indicate that there are 2 of them. Heptane, there's 7 carbons. Watch this. 2, 3, 4, 5, 6, 7. Count the vertices. There are 7. 1-chloro. Well, I'm going to say this is 1. So here we have a chlorine atom. And then we have 1,2-dimethyl. So a carbon 1 and carbon 2. I have a methyl group. So here's carbon 1. Another methyl group right over there. And then we have here 2 right over there. So we have here 1-chloro, 1,2-dimethyl heptane. Okay. All right. Now draw the condensed structural formula for 3-bromo, 1-chlorobutane. We have a butane, 4 of them, 2, 3, 4. The third carbon has a bromo, 1, 2, 3. Here we go. B, R, and then 1-chloro, 1, chloro. Okay. This here is written wrong. This should go here. And this one should go here. The text didn't turn out right. Right there. Here it is. Right there. Or we can do the skeletal formula right over there, as I love doing it because it's much easier. Right there. You can do these on your own. All right, properties of alkanes. The different uses of alkane compounds results from their physical properties, including their solubility and density. The solid alkanes that make up waxy coatings on fruits and vegetables help retain moisture, inhibit mold growth, and enhance its appearance. So alkanes with one or more carbons are gases at room. 1, 2, 4 carbon atoms are gases at room temperature and are widely used as heating fuels. For example, methane, ethane, propane, and butane are gases. However, the longer they get, the more interaction that they can have with each other, and so therefore these tend to be highly volatile liquids at room temperature, making them very useful as fuels like pentane, hexane, heptane, and octane. Octane, as you can tell, has 8 carbons. Now, alkanes that have 9 to 17 carbons tend to be liquid with higher boiling points. The reason why, because we have van der Waals forces, or we have here if we were to have other long hydrocarbons there, they tend to be stuck together, interact together, and so therefore more energy is needed in order to break them and split them apart to make them into gases. That's why they tend to be liquids and require a lot more heat energy, i.e. higher boiling point. And these are found in major oils, mineral oils, kerosene, diesel, and jet fuels. Now, alkanes with 18 or more carbon atoms, known as paraffins, are waxy solids at room temperature. Now you have a tremendously long one. So many places where that hydrocarbon, the alkane, can interact with other alkanes. And therefore, you need a lot of energy in order to get them to peel away and become a gas. Petroleum jelly, also known as Vaseline, is a semi-solid mixture of hydrocarbons with more than 25 of them. Okay, and these, of course, are waxy substances. Solubility and density of alkanes. Alkanes are nonpolar, insoluble in water, less dense than water, flammable in air, and found in crude oil. If there is an oil spill in the ocean, the alkanes and the crude oil do not mix with the water, but they do start to float on the top and produce a very thin film. A lot of times the oil, because it is on the surface, will disrupt the surface tension of the water. Okay, so there we go. Oil spill. For example, in April 2010, an explosion in an oil drilling rig off the coast of Mexico caused the largest oil spill in U.S. history, spilling at its maximum about 10 million liters of oil a day. And so there's mechanical, chemical, and microbiological cleanup that was used in order to remove that oil from that particular spill. Now, combustion of alkanes here, it reacts with oxygen gas to make carbon dioxide and water. So here we go. We have heat products here, carbon dioxide and water, and the CC bonds in an alkane release energy and are broken in those combustion reactions. For example, methane is a natural gas used to cook our foods on gas stovetops and to heat our homes. Butane is often used in portable burners. It undergoes combustion and produces enough energy to cook food also. For example, you have here butane mixing with oxygen and add a little bit of heat. And get started, produces carbon dioxide, water, and of course some energy, often used in camping. Propane is a fuel often used in barbecues as well. So you can see here, if we were to write the balance equation for the complete combustion of propane, you can see here propane, C3H8, and oxygen giving us carbon dioxide and water, not balanced yet. So in this example, what the textbook is telling us to balance the carbons, as they are the easiest. We have 3 carbons here, so add a 3 coefficient there, and then balance the hydrogens. So you can see we have 2 hydrogens here versus 8, so add a 4 in order to balance that out. But unfortunately here, what happened by adding the 4 in front of that water molecule, we have 8 water molecules, but we now have 4 more. 4 plus 6 gives us 10, so therefore we need to have 5 in front of the O2 in order to balance that equation out. So here's the thing about balancing equations. Don't panic about it. You're probably asking yourself, oh, how is it that some people can really balance these equations so fast, and I'm sitting here forever trying to figure it out? Don't worry about it. Well, actually, you should worry about it if you're not balancing them in good time for an exam. But when you first start out, it's going to take some trial and error. It's one of those intuitive skills that you pick up when you look at it. And you can definitely, after much and much practice, you'll be able to figure out what strategy works for you. In this case, the textbook is recommending balance the carbons, the hydrogens, and then balance everything else. Let's go ahead and talk about alkenes and alkynes. Alkanes have carbon-carbon single bonds. Alkenes have carbon-carbon double bonds. Alkynes have carbon-carbon triple bonds. So as you can see here in this image, we have ethine, which is a suffix for an alkyne. This is commonly known as acetylene and is used in welding, in which it reacts with oxygen to produce flames with temperatures above 3,300 degrees Celsius. This here is ethine. Between that carbon-carbon, we have one sigma bond and two pi bonds right over here, and three bonds right over there. So that would be an alkyne molecule. Alkanes and alkynes are families of hydrocarbons that contain double and triple bonds, respectively. So once again, alkenes mean double, alkynes are triple bonds, and are called unsaturated hydrocarbons because guess what? We don't have 4 bonds in every carbon. One of those carbons, at least one of them, may have a double bond with something else. Now you're thinking, wait a minute, isn't a double bond considered 2 bonds? Not quite. A double bond, while it contains 2 different kinds of bonds, one is a sigma and one's a pi bond, they're considered as one bond. If you get what I'm saying, it's considered one bond. It's just called a double bond. Now, a triple bond contains something known as 1 sigma and 2 pi bonds. So we have 3 bonds going on here, but they collectively are known as 1 bond. Okay. So therefore, those carbons do not have 4 different substituents to them, so therefore they are not considered saturated hydrocarbons. Now, these hydrocarbons also react with hydrogen gas in order to increase the number of hydrocarbon atoms and therefore can become alkanes. Once again, let's take a look at alkenes that contain 1 or more carbon-carbon double bonds. In ethene, we have here a double bond between those 2 carbons. Now each carbon atom in the double bond is attached to 2 hydrogen atoms, and it gives it a trigonal planar arrangement. If you were to get your molecular models kit and draw out ethene, you're going to see that all the atoms are flat. Okay, like as you see in this image, they're going to appear flat, not even tetrahedral. You won't have little atoms sticking out everywhere in 3D. They're going to be completely flat. Okay, so check that out. It's really interesting. Ethene is a prime example, as you saw here in the previous slide. Ethene is a prime example of a type of alkene. It is a very important plant hormone involved in promoting the ripening of fruits such as bananas. So the more ripe a fruit is, the more ethene it definitely produces. And one of the strategies in which to get fruits to ripen faster is to get a really ripe banana or some really ripe fruit and throw it in a bag of unripe fruits, close it up, and let that ethene molecule diffuse on out throughout that entire bag. And by doing so, it quickly ripens up those fruits. Okay, and ethene also accelerates the breakdown of cellulose in plants, which causes flowers to wilt and leaves to fall from the trees. Alkynes here contain 1 or more carbon-carbon triple bonds, and in ethine we have here C2H2. So the formula for an ethine here is C with an N, or X number of carbons, H, okay, H2N minus 2. So that is kind of the formula for an ethine. So the 2 carbon atoms here are conducted by a triple bond, and each carbon is also bonded to 1 hydrogen atom in ethine. Each carbon atom in the triple bond has a linear arrangement with bond angles at 180 degrees. So completely like this, like my pen. Okay? So just keep that in mind. Just like in ethene, it's completely flat. Same thing with ethine. It's also completely flat. It's just like a pen. All right, so identify the following compounds as either an alkene or alkyne. As you can see here, we have our skeletal model. We have 2 bonds. This is a double bond, so that would be an alkene. And then we have here a triple bond, which is an alkyne. Now, here's one thing that a lot of students kind of forget. This here is also vertice. There is a carbon atom right over there. But a lot of students kind of misunderstand. They think there are 3 carbon atoms at the end of this thing. There's actually only 1. But between this carbon and this carbon right over here, we have a triple bond. So be very careful. A lot of students think that if they don't see like little bend or little vertice here that there isn't a carbon. For triple bonds, there is a carbon atom, one here on the left and one here on the right of that. Remember that, guys. It's often missed on an exam. Now the IUPAC names for alkenes and alkynes. Again, alkanes is ane, alkenes with an ene, and alkynes with a, guess what? An ine at the very end of it. So we have here alkane, we have ethane versus ethene versus ethyne. As you can see, the double and triple bonds defines a kind of alkane, defines a kind of alkene or alkyne molecule that it is. So the same rules apply. Always identify the longest carbon chain in hydrocarbons, look at the substituents and give the lowest number to the substituents as you can, and then identify them. Now, if we were to look at our priority chart here, alkynes and alkenes have these different priorities right over there. So check this out. You can see here, write the IUPAC name. If we were to identify the longest carbon chain, I see it's right here. Okay. Now I want to identify where that double bond is, so we're going to treat it like a substituent, even though it's kind of not. We're going to label our carbons here 1, 2, 3, 4, and then 5. So we definitely have a pent. Definitely have a pent right over there. It's on the 2 carbon, so we can have here a 2-ene. Okay, we can have there a 2-ene. And then we have here on the 4th carbon a methyl group, so it's 4-methyl. Okay, my pen's not working with me. So you're probably wondering, why can't we number it the other way, like 1, 2, 3, and 4? Well, the reason why is because the alkene group compared to a methyl group has a higher priority compared to that of an alkane. So we want to make sure we keep that higher number at its lowest priority. Okay, so we have there 5 carbons, 6 carbons. If we were to name it, it would be a 2-pentene. Yes, 2-pentene, and then we have to consider that substituent 4-methyl-2-pentene, as I've mentioned earlier. Okay. All right, cycloalkenes, just like cycloalkanes, except for this cycle, we do have a double bond, and we need to tell the reader, or need to tell the scientist, where that double bond is. So cycloalkenes have a double bond with a ring structure and are named by assigning the double bond to be between the carbon 1 and the carbon 2 when a substituent is on the ring. And once again, the rule of thumb here is that since the alkene is a higher priority compared to that of alkanes, we want to keep that at its lowest substituent number. So we want to start here with the number 1. Now, one of these 2 carbons will be number 1. It's going to be this one here, is because as we number across to the left, 1, 2, 3, then this methyl group will have the lowest priority, versus here 1, 2, 3, 4, which will give it as 4. Or if we were to name this as a number 1, if we were to go the other way here, 1, 2, 3, 4, so it would be incorrect. You need to number this like the number 1 right here, and then cross through the double bond before you can get to the second carbon. You can't number this 1 and then call the next one 2 and expect us to know that the double bond is on the opposing end. So you put the number 1 here over the first carbon, and you have to cross through the double bond and then number the second carbon. This here would be an example of a cyclopentene. Okay, you could say cyclopent-1-ene. However, it's implied that double bond there is on that carbon 1 and that carbon 2. And then, of course, at the 3rd carbon here on that pentene, cyclopentene ring, we have a methyl group. Okay, so the carbon atoms in the ring are numbered to give the double bonds numbers 1 and 2 the lowest possible number in any substituent present. All right, so when naming these alkenes and alkynes, we definitely have here a cyclohexene. We can say, I could say cyclohex-1-ene or something like that, but it's already implied, don't need to do that. And then we can definitely have here 1, 2, 3. This is definitely a pentene. We can say 3,3-dimethylpentene. because we have 3,3, two methyl groups, 1, 2, so 3,3 dimethyl, and then pentene. We can do, I'm sorry, cyclopentene, 3,3 dimethyl cyclopentene. I could say 3,3 dimethyl cyclopent 1-ene, but it's already implied. Okay? All right. Moving on. Remember that double bond that I told you about? Okay, the atoms or groups of atoms attached to carbon atoms on a double bond may form two different kinds of structures known as cis or trans structures. So if we were to take a look here, take a look at this carbon-carbon double bond. You could have the chlorine above or below the double bond, depending. If that chlorine atom or that substituent is on the same side of the carbon-carbon double bond, therefore they would be known as cis for same. If they happen to be on opposing ends of that double bond, they're known as trans. So in an alkene, the double bond is very rigid and it cannot rotate. Okay, try on your molecular models. Okay, try to double bond those, see if you can kind of spin it around like you could have done in an alkane molecule. You can't do that. Okay, because that pi bond locks into place. Look, if we were to have 101, I could spin my fingers around like this. But if I were to lock a second one in there like this, I can't spin my hands around. Okay. All right, so when this is there, when there's a possibility of cis-trans, we have to indicate that in our nomenclature. So cis-trans isomers have different physical and chemical properties. You can make a double bond with your fingers with both thumbs on the same side. This would be a cis versus this is a trans. In a cis isomer, the alkyl groups are attached on the same side versus that of a trans. The groups in the hydrogen atoms are opposed in opposite sides. As you can see here, the two substituents are on the same side of the double bond. That's a cis versus that here, it's a trans. And this molecule here known as cis-2-butene versus that of a trans-2-butene. They're on opposing sides. Now, many insects emit minute quantities of chemicals known as pheromones because they're hormones of the air, so known as pheromones, okay, to send messages to others of the same species. Now, pheromones not necessarily used to attract the opposite sex, but they can also be used to warn the same species of approaching danger, or like in ants, they use pheromones in order to kind of make a trail. And the effectiveness of many of these pheromones depends on the cis and trans configurations of the double bonds in the molecule. One pheromone, known as a bombicol, is a sex pheromone produced by the female silkworm moth, and it contains one cis double bond and one trans double bond. The cis is right here, 1, 2. But then the trans is right here, 1, 2. So it contains cis and trans double bonds. Now, when naming cis-trans isomers, the prefix of cis or trans is placed in front of the alkene name when the compound is a cis or trans isomer. You can see here, we have here 1,2-dibromoethene, 1 carbon, 2 carbon. So it's 1,2-dibromo. It's an ethene, so 2 carbons are ethene. It's a double bond. And we have to indicate if it's cis or trans. So it's going to be cis 1,2-dibromoethene. Versus that here, we have a trans 1,2-dibromoethene because the bromines are on opposing sides. You can go ahead and name these molecules on your own. All right, addition reactions. The commercial process of hydrogenation is used to convert a double bond in vegetable oils to saturated fats, such as those in margarine. So in alkenes and alkynes, the double and triple bonds are very reactive. And the reason why, check this out, if you were to draw out that double bond here, so we have, gosh, this is going to drive me insane. Okay, so think of this as a 3D model of a ethene molecule there. One hydrogen's in the back, one's in the front, and we have that double bond there. What's amazing is that even the sigma bond, there's something known as a sigma bond, that's a signal bond, is connected directly carbon to carbon, but above that and below that we have pi bonds. Okay, you see this? You see this above and below, we have a pi bond. These bonds, even though the molecule ethene is kind of flat, like this, but above and below we have those pi electrons. They're known as pi electrons sticking out from above and below it. So these pi electrons, like sticking out, they can definitely go and attack different kinds of molecules out there. Therefore, that's why they are very reactive. They just stick out and are easily broken, providing electrons in order to form new bonds. So hydrogenation here is when you take an alkene and you mix in hydrogen gas, and with the catalyst platinum, nickel, and PD, you can form there an alkane. And same thing here with the hydration. If you were to take an alkane and mix it with water, you will produce and use a strong acid, you'll definitely be producing an alcohol. So those are a summary of addition reaction. What's being added? Hydrogen atoms into the molecule. You're changing an alkene and becoming an alkane, changing that double bond, breaking that pi bond, and then putting two hydrogens on each one of those carbons. So here is an example of that hydrogenation atoms. You can see we have an ethene molecule mixed in with the hydrogen gas. You must have platinum, nickel, or PD in the reaction, otherwise it won't happen. And so therefore that double bond here is going to need to break up, and then the two hydrogen atoms there start to bond to it. Okay, we have here a triple bond mixed in with hydrogen gas in the presence of a catalyst to speed those things up. We will definitely have there it becoming a saturated hydrocarbon. Okay, write an equation for the hydrogenation of 1-butene using a platinum catalyst. That is quite simple here. We can draw out that structural formula. And then we have here the condensed form, and then we have here the hydrogen gas mixing with platinum, therefore breaking that double bond and forming that alkane molecule. Now, hydrogenation of oils, adding hydrogen gas to double bonds in vegetable oils produces compounds with higher melting points in the and also solids at room temperature, such as margarine, soft margarine, and of course shortening. As you can see here, we have oleic acid that is found in olive oil. And if we were to add hydrogen and insert in a catalyst, in this case platinum, we can form stearic acid, and therefore it breaks, it completely saturates that double bond into becoming single bonds. Okay. In the addition of platinum, this bond will definitely break, therefore forming single bonds. And same thing here with the cyclopentene, adding hydrogen gas in the presence of platinum will definitely form that single bond. Now here's the thing though, what you are not seeing is that in this reaction, it is a platinum plate, and this platinum plate, or nickel, whatever, has hydrogen atoms all sticking out. And when a alkene group, in this case, comes in, we have those pi electrons that are sitting over, they come and they attack these hydrogens and snaps that double bond open, and therefore forming an alkane. So that's kind of really what's going on. Why you need platinum? Because that platinum acts as a bracer with tons of hydrogen atoms on it, and it grabs those hydrogens and it snaps that double bond open and forms those single bonds. So we're going to talk about hydration reactions. In hydration reactions, an alkene reacts with water, H2O, to form an alcohol. So you can see here the hydrogen atom from the water forms a bond with the carbon atom in the double bond with more hydrogens. So here we go. As you can see here, in the presence of water, this double bond here, which the pi electrons, what it's trying to say is that these pi electrons go ahead and attack this partial positive hydrogen and dunking those covalently bonded electrons to that hydroxyl group, forming a hydroxyl forming a hydroxide ion. And then the hydroxide ion is therefore, in the presence of other molecules there, that double bond is also going to grab a hydrogen atom from solution as well. Okay, it's going to grab that. And then therefore the hydroxide atom is going to bond right on back. Okay, it's going to bond right on back over here, because now we have a positive charge in the carbon. It's come on back, therefore forming this alcohol. Okay. And same thing here with the ethene. The double bond here is going to bind over to the hydrogen atom, therefore dunking this dunking these two covalently bonded electrons over to water. Now the hydroxide ions right over here. Now we have what's happened. We have an intermediate CH3 with the CH2, but because it's missing a bond, therefore it risks a positive charge right on that carbon there. So therefore the hydroxide ion very attractive to that positive charge is going to bind there and form that final fourth bond with the hydroxide, therefore leading us to that alcohol. So just kind of showing you the mechanism on how these reactions happen. Okay, you can do these problems on your own. Okay. All right, aromatic compounds, the things that make things smell good. Michael Faraday, responsible for the Faraday constant, but I'm not going to get too much into detail about that, isolated a hydrocarbon known as benzene, which consisted of a 6-carbon ring with alternating double bonds. Is extremely important. Also, you might see it drawn as this. That will also be resembling of a benzene ring, and the molecular formula here is C6H6. Now, a benzene is an aromatic compound because the word aromatic means that every other bond is a double bond. A ring of 6 carbon each bonded to one hydrogen atom, and it is a flat ring structure because remember, double bonds, carbon-carbon double bonds are flat. Use your molecular models if you can't see it. A flat ring structure drawn with 3 alternating double bonds, and it is represented by 2 structures because the electrons are shared equally among all carbon atoms, and is represented by a skeletal formula using a circle at the center instead of alternating bonds. So you can see this is one way to resemble that, or you can do what I did earlier, which is just drawing these 3. A circle is the same thing as drawing this. Okay. Aromatic compounds containing a benzene ring and a single substituent are named as benzene derivatives. Since a ring contains only one substituent, the ring is not numbered. Now, some common names such as toluene, aniline, and phenol are allowed by IUPAC rules. So, for example, this would be known as toluene, where it's a benzene ring attached with a methyl group. Aniline here is a benzene ring attached with an amine group. And we have a phenol, which is a benzene ring attached with an OH group. O is kind of a hint right over there indicating their alcohol. So, for example, when naming these, we have here chlorobenzene. We only have one substituent, so the 1 is implied. 1,2-dichlorobenzene, 1,2, 1,3-dichlorobenzene, and 1,4-dichlorobenzene. Okay, the benzene ring is numbered to give the lowest numbers to the substituents. Now, when a common name such as toluene, phenol, or alanine can be used, the carbon atom attached to the methyl, hydroxyl, or amine group is numbered as carbon 1. The other substituents are named alphabetically. Okay. All right, so you can see here 3-bromoaniline. So we can see the amine group right over here is given its 1. And the reason why, check this out, look at this. Anything with amines right over here has a higher priority compared to that of chlorines and alkanes, such as methyl groups. So amines have a higher priority. They will get the first number right over here. So this is 3-bromoaniline. We can also name it here. The alcohol group gets a priority because according to our chart, alcohols are higher priority compared to that of alkanes or even halides. So therefore, that 1 belongs to alcohol. This would be 4-bromo, 2-chloro, phenol. We can also have here the methane group here has a higher priority, and the reason why, again, alkanes are higher than that of halides, so therefore they will get the first priority right over there. So this would be known as a chlorotoluene, toluene, so 2,6-dibromo, 4-chlorotoluene. Now, toluene is used as a reactant to make drugs, dyes, and explosives such as trinitrotoluene or TNT, very commonly seen in cartoons or old-fashioned cartoons back in the old day. The benzene ring is also found in some amino acids, which are the building blocks of protein. So if we were to take protein and break them down to their individual Lego blocks or building blocks, they would be called amino acids. Phenylalanine is a very common amino acid that is found out there. Now, the benzene ring is found in many pain relievers such as aspirin, acetaminophen, and ibuprofen. I can't even pronounce that today. And in flavoring such as vanillin. And some of you guys have already seen that in lab. So you can see ibuprofen, vanillin, acetaminophen, and aspirin, which is right there. Trying to pronounce that. You can go ahead and name these on your own. Okay, those are the correct names right over there. And here is that concept map in introducing organic compounds. So I hope that you found this lecture informative. Hopefully that you got a copy of that chart, because you definitely might want to know the priority orders of those particular compounds when naming alkanes, alkenes, alkynes. There are many other kinds of names out there. Once you know these rules, naming alcohols, amines, or whatever are going to be very simple, because you already have this chart in your notes and ingrained in your memory. Anyway, so I hope that you found this lecture informative, and I hope that it helps get you caught up with whatever materials that you need in order to do your mastering chemistry homework. Until next time, until lecture, I will see you then. All right, good luck studying.